So what came out of that, out of the 2000s, were 90s and 2000s with a few dominant architectures. There were ARM and MIPS being two major ones, and there were Hitachi Super H, there were other architectures, but these were the dominant. And latest one we're all talking about, RISC-V, instruction set wants to be free, a revolution. So we'll talk about RISC-V for now, but this will just give you a history of where the CPU came from and where we might be going. So RISC-V's value is it could be as simple as possible. I could just have a 32-bit processor, RV32i, and I could do everything in software. Or on the right-hand side, I could add a lot of extensions. So do I need a hardware multiplication? Well, I could do multiply by adding, but maybe I could dedicate some hardware, make this much faster. Atomic operations, floating point, both single and double precision, and so on. And what's most interesting, at least now in the RISC-V world, is a vector processing. It came into existence just as AI was becoming popular, and it is sort of targeted at applications. So let's look at traditional multiprocessor architecture in the world. Well, you have a single processor with cache and data cache, instruction cache, data cache, perhaps local memories, and CPU operates on that. You have the same processor or similar processor on the sitting right next to it, talking on the same bus. One of the challenges of this is since the main system bus is shared, main memory is shared, peripherals are shared, you lose some deterministicness. And that is going to be some of the Achilles heel of vector processor. So this is what the standard RISC-V vector architecture sort of looks like. It supports latest vector spec. Vector spec is almost final. Hopefully it's final soon. It supports standard integer and floating point data types. The RISC-V specification is very configurable. There is a vector length SIMD, the configurable lengths. And there are vector compute instructions and operations, both the start execution, whether it's retired or not, chainable and fully pipelined. And there's a dedicated vector load store unit to move the data in and out. But again, it goes to that main system bus that's shared with other processors. So this is how what it would look like in a high-level diagram. You have the CPU on top, vector processor that relies on the CPU. So it relies on CPU's load store unit, or shares CPU's load store unit with the vector load store unit. Problem, that AXI bus, main system bus, becomes a choke point because now you have multiple CPUs, vector processors, and custom accelerators all moving data in that AXI bus. And this is what would look like in the sort of neural network accelerator. Same picture, but you have complex of RISC-V instructions, complex of neural network accelerators. You might have a control processor, all sharing the system. Bus was already pretty much saturated with CPU data. Now we're adding a neural network data, which requires extensive sequential memory access. So how do we solve this? In CPU approach, this would be, hey, let's put larger caches in. I joke that cache is like the other cache. They could never have enough. So we're starting to see some vector processors with over 512 kilobyte level 1 cache. Well, that's also backed by level 2 cache, which needs to be 4 to 8 times bigger. That's even backed by level 3 cache. So now this vector unit, the logic compute engine is very small. The memories are just dominating. But that downside, real downside, is frequency. 512 kilobyte level 1 running at CPU frequencies, it's almost impossible to get very high frequency. So now you trade off frequency for performance. If you're running slower, you don't have memory problems, as much memory problems. So it's kind of a current issue. In the DSP approach, it actually worked. DSPs generally had dedicated multiple memory ports. what DSP relied on is predictable bandwidth, predictable latency latency for real-time operations. And real-time really means predictable. If I know I'm going to operate one operation every 5 seconds, then I know that it's predictable, dedicated, and I could plan my world around that 5 seconds. CPU, not so much. There's no guarantees. So the bandwidth is the issue. How do we solve it? And DSP is the right solution for this vectors. Vector is a class of DSP. So how does Andes go about solving this now? We have something called Andes custom extension option. Basically, this extension allows you to build new instructions, new coprocessors or connections, and new memories. So if you look at the bottom, you see the typical old way of doing it. I'll say 90s way of doing it. CPU goes on the bus to talk to an accelerator. Well, yes, that works, but again, puts a lot of pressure on that bus. And if you're worried about security, all your data is going to the main bus that's accessible. Or you could do a couple of different ways. With Andes, you could create a custom port to talk to the accelerator and custom instructions to control that accelerator as well. So it gives you a little bit more paradigm away from the main system bus, more predictable. We wrap this up with a nice software tool that could generate and model and verify these extensions. It's called Copilot. And what we create is something called streaming port. Streaming port is as wide, as narrow, as fast, custom dedicated port to talk to the external coprocessor or memory. We marry that with ACE pipeline or ACE custom instructions to control or send data to the coprocessor as well. So there are two custom extensions in this diagram. The streaming port to move the data and command port to send the command to control. Okay. Hardware is tightly coupled to the CPU. The data bus and the bandwidth, and most importantly, are dedicated and predictable. And you could create some DSP-centric, not CPU-centric operations like wraparound addressing or auto-increment, auto-decrement. So here's a CPU that encapsulates all this. We call it NX27B. It's a 64-bit processor, RISC-V plus Andes-specific extensions. It has 5-stage CPU pipeline, scalar pipeline, and then it does have big options, larger caches, 8 kilobyte to 64 kilobyte. Look at the hardware unaligned loads and stores. Most importantly, there are prefetching. DSP or vectors by the nature of the data is sort of sequential, so prefetching relieves some of the pressure on the bus. And then outstanding data accesses. There's a lot of data accesses. And we'll talk about that there are two ports. There's an axis system port, and then there's a stream port, custom port to move the data as well. Vector processor could get the vector unit could get the data from axis as well as stream ports. And this is what our CPU microarchitecture looks like. Currently, it supports RISC-V Vector 1.0 release candidate. Supports all the standard formats. Everything Andes does is RISC-V compliant. And then we added a couple of specific data formats for AI, bfloat16 and N4. Those are the sort of AI-specific data formats. SIMD, the computation unit, vector length, it's very configurable, as well as memory bandwidth. We natively support 256 bits. That seems to be the most common memory controller bus with configuration. Vector units, we treat vector unit like a coprocessor in that CPU, once it dispatches instructions, vector instructions to vector unit, we assume it runs to completion. CPU considers that instruction completed. There are multiple operating units. There are 8 operating units plus vector load store unit. So vector unit could do 9 operations out of order at the same time. It's chainable, fully pipelined, so we could do sequential operation. And we could load the data from streaming port we talked about. There's a RISC-V vector loads and store unit, And then there's a CPU load store unit, a streaming unit. Idea is to get a lot of data in, a lot of data out as quickly as possible. So we saw this picture. Our vector processor has, if you think of it as 3 different pipelines, we have a CPU, scalar CPU, we have vector processor, and ACE pipeline. And then this gives you a picture of our Copilot could generate all the housekeeping operations, and you only have to concentrate on the logic that you want to accelerate. Maybe you want to generate a auto-decrementing address pointers, or maybe wraparound, or maybe you just want to send a one command, very wide command to your coprocessor. Those things are all possible. And here's some of the sort of ideas. So this I borrowed from my old networking days. You could create a ping pong buffer for your network accelerator, whether network accelerators are shared with the CPUs or dedicated to CPU. While you're operating on one buffer, you could be filling and emptying the next buffer. CPU and vector processor keep going. Externally, you manage the data operations. Again, and these extensions and RISC-V vectors give you a lot of flexibility. This is where the scalableness comes in. First, we have this processing element on the left, CPU with a string port talking to NN coprocessor. And then we could just take this, implement it on the processor, because the processor and the neural network engine have its own high-speed data path. It's much easier and predictable to do a multi-cluster architecture. We program all this. OpenCL is only one multi-core programming environment. There's also other programming environments available. We also make it easy. Nobody programs in assembly anymore. So we have our assembly engineers create neural network libraries, or DSP libraries, in addition to the auto vectorization that the RISC-V community is working on. So here's some of the performance gains you could typically expect. 32-bit floating-point math, you could see about 20 times acceleration compared to standard C code running on a RISC-V processor. CNN functions, again, typically about 20x acceleration. And if you're really worried about matrix operations, convolutions, then we could even give you about 60 times acceleration. Vector unit is powerful compute unit, but it's only powerful if you could feed that compute unit. Think of it as big dragon. You don't want the dragon to go hungry. Thanks, Dave, for laughing at my dad joke. Now, we wrap this up with our software called Clarity. Clarity is low-level optimization pipeline viewer software. So you could ideally take a look at, am I losing my performance because maybe I'm waiting for data to load operands, or maybe there was a misprediction that if I juggle the instructions around a little more. So DSP engineers from history were always assembly engineers. I remember spending 2 years of my life after graduate school optimizing assembly code. So if anybody has a question on x86 assembly, I think I could still answer it. But Clarity tool makes it very easy to see the pipeline, each stages, and most importantly, where the stalls are. So that's the challenge that I see for RISC-V. It's not so much more compute for vectors. It's how you feed that vector engine, because the bus is already saturated just doing CPU things. Adding neural network engines really makes a system, you lose out of system performance. Any questions? Or if you have questions, put it on chat. Here's my email address. Feel free to email me. I I have a question here. Is it scalable with cache currency? Yes, it can be. That's where the level 2 caches and level 3 caches come in. It does add more. It does add more complexity to the hardware. However, there are some cases where you may be running Linux, smaller systems where you want to move the data. There's some dependency with us. Some of the vector instructions not interruptible, exceptionable. So there'll be some software workarounds, but there's no reason why it cannot be scalable with cache currency. Okay, if there are no more questions, feel free to contact me. Dave, I assume you're going to share slides?
So I am.
Okay.
I'll share directly.
So here's a man that I spent, seems like, last 6 months communicating. He's got some interesting...
Mostly over beer.
Yes. So he's got some insights from the user standpoint about RISC-V and RISC-V vectors. Dave, I will stop sharing. It's all up to you.
We'll share. If we did all of those parts right, you should be seeing...
Yes, we see your slide now. Perfect.
Hey, there we go. So as I was saying, we've been working together, Andy's and Luminous Computing, for at least 6 months on NX27V applications. My history involves the implementation of many DSP processors. And when I looked at the NX27V architecture and microarchitecture with John, I felt like I'd come home, because this RISC-V processor is really a DSP at heart. And everything that John just showed you, I think, kind of emphasizes that. So the applications that we're putting it to are essentially DSP applications as well. Sure, we call them neural net processing, but essentially they're DSPs. And so I completely agree with everything that John just said to you. So let's look at Luminous Computing's application briefly, and I'm going to confess at a very superficial level. So we're building large-scale deep learning accelerators. That's kind of our stick. That's what we're up to. And along the way, we've developed some very high-speed, low-power photonic multiply accumulate hardware that takes care of what would normally be the gem engine in one of these devices. And now I'm going to take a little moment for a thought experiment. So I want you to follow along with me here as I describe this thought experiment. Pretend that you're in a dark room and that you're holding a flashlight in your right hand. So you turn that flashlight on and you shine it at the wall. And you see this nice bright spot show up there. And suppose you have a flashlight in your left hand and you turn it on and you shine it at the same spot. And suddenly you're getting twice as many photons back from the wall as you were. So this is basically an addition operation done the old-fashioned physics way. If you also now consider laser light sources and modulators in front of those lasers, and if your modulator is pretty linear in voltage-controlled applications, you can put yourself together a multiplier. So if I have a multiplier and I have an adder, then I have a whole lot of the beginnings of multiply accumulate. Now, if I replace the flashlights with these laser modulator pairs, and I replace the wall with a photodetector, I now have something where I can combine many light sources together and get the aggregate addition of a whole bunch of multiplies. So picture doing that maybe 256 times, and keeping that in mind that light, the physics of light is such that these operations are happening really, really fast and can be done at very low powers. And so we have these almost instantaneous multiply accumulate blocks, except we have to run them through an A to D converter. The A to D converter is the limiter for how fast we can run all of this. The photons themselves are real happy running much faster. So basically we put an A to D converter and we put an accumulating register behind it, and now we can step and grab our inputs to those modulators, and along comes a whole bunch of very large multiply accumulate, much like you might do with a systolic array or something like that, except the powers tend to be a lot better. And so that is the technology that we bring to the table for for basically doing acceleration from multiply accumulate. Multiply accumulate is by far and away the predominant function that has to be done for machine learning. But it isn't the only one. So having a vast array of multiply accumulate is simply not sufficient. So computationally, one also needs other operators, and John also alluded to this as well. Things like ReLO or 10H, max pools, vector add, batch norms. All of these things require nonlinear and certainly non-physically implementable kinds of multiply accumulate kind of operations for the most part. And so we need a way to deal with these. And for example, take a look at the operators in a BERT large model. If you look at all the layers of BERT large and you look at all of the processing that's going on, there's an awful lot of multiply accumulate in it. But there's a lot of weird things that just don't fit into that paradigm. And so, so we just had to take a look at what are we going to do for the rest of this. And so what we did is we joined forces with Andy's Tech for RISC-V VPUs. And I'm going to show you the same charts that John did, but basically what we're doing is we're taking a whole lot of NX27Vs, as in many, and we're applying their vector processing capabilities literally as if they were DSP units. So we have very tightly coupled memories. We have a lot of very tightly coupled memory, and we are taking advantage of the ACE interface so that we get dual loads and stores. As you know, the algorithms of interest here almost always read to, operate, write once, or in some cases don't write for a long time. So load performance is really important to these guys. And having two independent storage access mechanisms is really good for us. And having one that deals with streaming is extremely useful for data coming back from, shall we say, photonic multiply accumulate. So we like this architecture a lot because in addition to the scalar processor, they have these two independent and essentially asynchronous pipelines that they operate on for instructions. And so there's a queue of vector instructions that I can punch a bunch of stuff into the queue and turn it loose and let it run while I go deal with programming the ACE pipeline to go issue commands to my external processor or actually move data on and off chip with the ACE interface. So this is like having three processors in one, and one of them has very high IPC. The vector processor itself has an IPC around, probably delivers around 5 or 6 instructions per clock when it's running full out. So all of these things are very DSP-like, and for us, perfect for our accelerators for neural net processing. And I'm really not going to spend any time on this because I think John did a much better presentation than I did. But let's look some more at what we're actually doing. So we're building systems with many NX27V VPU cores, and that is in the hundreds. And so a lot of vector processing capability. So when we throw something back from multiply accumulate, we can really process a lot of layer data very quickly, thanks to all of the features of NX27V. So we also have large amounts of DRAM per system, and large is, I mean, really large. And so we are moving data from various different places in the system into these cores to process. And we also have a large amount of SRAM per VPU. So each one of our VPUs is configured as basically a standalone DSP, a standalone vector processor. The data that it operates on is data that's very local. And so we can actually do all of this pre-planning that John was talking about for prefetching and all of those things. Works really well for these algorithms. We know a long time in advance on neural net processing what data we're going to need to operate on when we finally get around to operating on it. We also depend heavily on the Andy site IDE and GUI. And our experience here, we use it for both code generation. We use both their GCC and their LLVM deliverables directly, and we use them within the IDE. We use them in chip simulation environments, FPGA environments, and ultimately in real silicon. We use them a lot for debug. Unfortunately, we still put those bugs in there. And then we use them a lot for their simulator. And I think this is probably the greatest thing about the Andy site toolchains is what John showed you earlier, which is the annotated simulator that shows us exactly where an instruction sequence is stalling. And I'm going to confess, we actually do write a lot of our code in assembly language. And I know that's kind of old school, but when you're a DSP person, as John alluded, you write in assembly language. And we certainly have algorithms that are hand-tuned in assembly language for vector processing. There you go. And I also like the profiling, which is the tool he showed you. We also use some of their other IP products, like their Linux engines and their RV32 product that we use for our hardware root of trust. In short, all of our digital computation that is programmable is done with Andes IP. So Luminous Computing and Andes, well, we needed an IP provider with a complete portfolio, and we needed one with leading edge VPU implementations. Certainly we're getting that. And we needed access to bfloat 16. A lot of our intrinsic data processing is in bfloat 16 data type. And so we needed somebody who was really up to running with that and using it in a VPU format. And that was one of the leading factors that led us to initially approach Andes. Later on, we found many other reasons why we were glad, but this is the one that sort of brought us to the table. We needed a solution that had really strong software tool support. And I think you saw in John's presentation the capabilities that Andes Site and profiling tools that they offer provide for actually real diagnostic profiling of where the cycles went when you don't know where they went. We also needed a partner that would support us every step of the way, and that definitely is Andes. The test chips we developed have simply worked for us. We've had some difficulties, and every time we have had difficulties, Andy stepped in. Really excellent FAE support. The guys that we work with in their support staff and John are really well versed in understanding their product and understanding all their software tools and their RTL IP as well. They provided us with quite good training. And when we have run across a software bug or two, they've gotten it fixed really fast. They've also scheduled and delivered tested RTL fixes for us on the various drops that they've provided us, all of which speaks to a very organized design and release flow that they operate in-house. And finally, they've hand-tuned some VPU algorithms for us, things we specifically requested. So I call these a few freebies that they threw our way. But when we thought there was a better way to do things, but we weren't seeing it, we handed it back to Andes, and they put their guys on it and showed us how to save a few cycles here and there. So really all around, just good interaction and good interfacing. I'm going to open up for questions. I don't think I hardly used my time at all, but I'll fill up the rest of it with questions if you have some. And for that, I'm going to have to find my Zoom screen. Come on, chat, where are you? There you are. So is it scalable with cache coherency? I like it. I like that one. Is that an Aloha shirt? Yeah, that's an Aloha shirt. My wife and I lived in Hawaii up until March of 2020, which got us back just in time to quarantine. But I still kept my Aloha shirt. So yes, you're right about that one. That was the easy question. The question on cache coherency is an interesting one. This is back to the notion of, are we a CPU or are we a DSP? DSPs almost never succeed with caches. They almost always fail in cache miss hell. Basically, people trying to figure out how to tune algorithms so that the caches actually work for you. We're not relying on caches to any great degree. We have an L1 cache. We didn't choose to use L2s and L3s. We have direct access to large blocks of SRAM. We have paid a little bit of a price and performance for doing that, but overall, we haven't lost anything to cache misses, and we haven't lost anything to cache fills. So overall, we think the total issue is quite scalable with this approach and not needing the cache coherency. Now, as far as coherency is concerned, we don't like coherency designs. The reason we don't like coherency designs is because we're a DSP. If you are going to have cache coherency all the way across L2, L3, and an L3 that might be on a different chip, or at least part of the L3 might be on a different chip, you pay a tremendous penalty for getting to it. And you spend a lot of power keeping all those caches coherent. And all of those things are things that don't buy you anything in a DSP. And so none of our VPU designs are coherent. We have an L1 cache, we don't have L2s, and we sure as heck don't go cache coherent across chips. So there's a chat question here that says, I don't quite understand how you handle nonlinear operations, relo and tan, using vector extensions. This is exactly where we ask for help. So I sent a query off to Andy's about 3 weeks ago and said, look, guys, I don't think we're getting the 10H performance that we need to get out of the vector engine. Can you help us out here with an implementation? And it turns out that a fairly short Taylor series expansion will give you the kind of 10H performance that you need. And by golly, you can do it in parallel on a vector processor. And I think I hit the end of the questions. Well, John, you still owe me a beer.
Sure, anytime. I would have bought you tonight, but I'm not in Austin.
Yep. So anyway, I think that my email is available to you. I don't know if I had it on the slides or not, but it's pretty easy. It's dave@luminouscomputing.com, and you're very welcome to contact me there and ask additional questions after the fact. So with that, I guess I'm going to turn it over to Kat and let her talk to you about how you make simulators run really well. So I think I'm done here.
Thank you, Dave.
Sure. Stop sharing.
Thank you, Dave. Let me share my screen. Wow, how do you fill those shoes? DSP engineer, assembly engineer, and then a VP who designs in photonics. So I decided to go with my Aloha theme. So everybody see my lay here. And Megan, I didn't get the Aloha memo, but I found my lay. Hello, everybody. I'm Ketchi. I'm a senior account manager with Imperas Software. And today my topic is, yes, about software development for AI SOCs using virtual platform. This is my agenda, an overview on Imperas and why I use virtual platform for AI software development. And I'll hand over the time to my colleague Manny Wright for a Mobilenet demo. And then we'll open the floor to Q&A for all three speakers. Andes and Imperas has a tight partnership. We work together in the RISC-V community on compliance and verification. Andes certifies Imperas models and simulator as a reference for Andes RISC-V course. Here are 2 quotes from Andes executive to endorse our modeling of the vector extension and also the P extension. Quick introduction of Imperas. We are a market leader of ISA reference models, simulators, and tools. We use by world-leading chip and system companies across several disciplines. We have a successful university program, and we are an active supporter of open source teams. We are a private company based in UK. Profitable, has been in business for over 12 years, and we support customers worldwide. Imperas OVP RISC-V processor models are, I think, the best in the industry. We have a very rich portfolio of processors. As far as RISC-V goes, we have models for envelope models of all the rectified or near rectified specs, including privilege and debug modes. We support all the ND's cores, including NX27V. Now we see a lot of our customers, they add custom instructions, custom extensions, registers into their RISC-V processor. So we have developed an elegant methodology for them to easily add that to the Imperas models. The features are added into a side file so that doesn't perturb the verified base model. And magically, because they're using our environment, the models would work magically with our tools for effective profiling. Now, on the right-hand side, you see ovpworld.org. That's an open source site that we run for supporting all users that use RISC-V. So please visit there. There's a lot of resources and videos there. Our models are developed using test-driven methodology. Now, quick word on what is a virtual platform. The virtual platform is a set of instruction-accurate models that reflect the hardware on which the actual binaries will execute. So it could be as simple as a one-core processor SoC, and it goes up to the entire board. There's no physical limitations. One can control all the peripherals just like you're using it in hardware. And we also have features that allows our users to leverage the workstation resources. So for example, the resource of a keyboard, mouse, screen can all be used for the simulation. Imperas simulation is very fast, and we typically boot Linux on a virtual platform in less than 10 seconds. On the right-hand side, I'm just showing an example of an Andy's Imperas extended platform kit. That's a mouthful. Basically, it shows an N25 that boots FreeRTOS, and also an quad-core AP that boots Linux. And this kind of extended fixed platform kit can be easily handed over to the software team for them to start software development early. So this is our software development environment. I already talked about fast processor, our simulator, and let me talk a little bit about our tools. So in the diagram, you see the virtual platform consists of our CPU models. It's connected with bus and peripherals, memory. So the whole thing is a virtual platform. The virtual platform connects to our simulator engine through API. And our engine also has what we call a slipstreamer API that supports building of tools. Out of the box, we provide two top-of-the-notch tools for complex software development. One is MPD, multi-processor development for platform-centric debugging. And the second one is VAP, verification, analysis, and profiling tools for software analysis. We have probably 2 dozens of tracing functions. With MPD, we provide peripheral introspection, so very powerful tools. Our customers can also build on top of the slipstream API to build their own custom tools. And they can also use other favorite tools such as GDB, IAR, and so on. All right, let me switch gear to talking about AI software. Now, we think that virtual platforms are perfect for AI software development and test. Why? Because today, the real workload, the exploration starts in the cloud. The data scientists, ML engineers, they run in the cloud lots of runs to test real-world data sets. Now, the next step is to partition out the hardware piece. And because cloud is by nature multi-processing, parallel processing, so it maps very well into multi-core system. So now you map that onto AI SoC or a complex device like a Luminous device. Now there's a chicken and egg problem. So you got such a complex piece of hardware and lots of software to control the workflow. But the hardware takes a bit of time to become. So what does the software team do in the meantime if the hardware comes back? Now, so we think that the virtual platform offers a very good solution so that the software team can run real AI workload on top of the virtual platform even before the hardware is ready. And they can do some hardware-software co-design as well. They can iterate the software development test using this virtual platform. Well, John and Dave already talked about the different architectures, so I'm not going to dive in much on this slide. The gist of this slide is to show that the complexity and the variations of AI hardware, right? With different sizes of processing elements, different features within the processing element core, and also different configurations. For example, some with an accelerator, some with custom comms features. And the message I want to communicate here is that Imperas has the power and flexibility to model all types of AI hardware. Now, I talked about custom instructions, custom extensions, and Andy's also talked about that. So we actually work very well together to help our customers to build these custom instructions. So the flow can go roughly like this. So use Imperas for upfront architectural exploration on a IA instruction accurate simulator. So for example, you can profile your C application with the base model, identify where the bottleneck is, where the hotspot is, and consider developing a custom instruction to alleviate the hotspot. So then you can add that custom instruction into our model, iterate with the C application. Once you're happy with that custom instruction, then you can dive into the Andy's ACE tools for cycle accurate analysis and actually implement the custom extension. In parallel, as I already alluded to, you can build the virtual platform with the now extended with the customizations, processor model to help with the software and the test team. From our experience, we see that software development is the critical path for AI, ML, SoC projects. It's so complex. You have to find an optimum balance between the PPA. And there are so many different scenarios that one needs to try it out. So there are hundreds and hundreds of scenarios, hundreds of benchmarks to run. And so that results in lots of iterations and tests. If the traditional method is followed, sometimes our customers wait till there's FPGA, RTLs ready, FPGA, months of time might be lost. So we think a virtual platform would be able to accelerate the schedule by a lot. Well, zooming out a little bit, not just for software testing, there's also the whole schedule, quality, reliability, especially required by safety critical systems like a car, and the power requirements from small IoT. So we hear that from our customers that the software engineering task is now becoming pretty as far as project management goes, it's so hard to measure their accuracy and resource and even identify the delivery risk. And these are all things that a virtual platform can help with because it lowers the risk and brings the software development curve up front. Now, in order for us to claim that we are very good with AI simulation, the performance is important, right? So let's take a look at some of these numbers. Our simulation on the single core, single thread performance average to be about 1,000 MIPS overall, and that's on a 24 core single thread performance Rhinestone. So it's roughly 40 MIPS per core. And we have a method to provide parallel simulation. So it depends on the application, the performance can increase by 2x for 4-host x86 core host machine. And we designed our simulation to use very little RAM, and so it scales up very well. We have run simulations of, our users have run simulations of platforms with up to 1,024 cores. Another example is actually a joint customer with us, a joint customer of us and Andy's. That customer is an AI SOC customer. They have more than 150 cores, a mix of scalar and vector processors. And the results of running on Imperas, it runs at 500 MIPS and allows the hardware platform configuration, reconfiguration, and architectural changes. So it really gives them fast, rapid decision-making process. And the software was up and running in our environment 1 year before the RTL commit. So at this company's site, at this customer site, the Imperas model has become their functional executable that they pass from team to team to benchmark their software. That's my last slide in closing. I've mentioned that our tools are very high-end, very top-notch MPD and verification, analysis, and profiling tools, fast simulation, big processor library. And with a virtual platform compared to the hardware, there are a lot more things that you can do. For example, being able to control it, full observability, repeatability, automation of tests. In short, it shifts the whole schedule left, shifts left. Now that's all I have, and I hand over the time to my colleague Manny Wright for a Mobilenet demo. And after her demo, then we'll open the floor for Q&A.
Let me now show you how it works in Imperas virtual platform. For this demo, I'm going to run a computer vision AI application Mobilenet V1 on an Andes VPU, the NX25V processor. The application is compiled as bare metal. This Mobilenet application is written to utilize the RISC-V Vector extension instructions. Each convolution layer, both the depth-wise separable convolution and the point-wise convolution, have been vectorized to take advantage of the processor's parallel hardware. This demo is to pass an image to the Mobilenet model, which has been trained on the ImageNet library, and let it identify the picture. So in this case, the picture that we're going to feed to the Mobilenet is of this picture of a coastline with a castle clearly visible. This is a 224 by 224 pixel image, and it has been pre-processed to the format expected by the Mobilenet format. So now let me just show you how it works. Because the application is a bare metal, so I can simply run it in our instruction set simulator. So here I'm invoking the simulator itself, the ISS, on my laptop, running on Windows platform, and all the Imperas tools also run on Linux platform as well. And so I'm telling the ISS that I'm going to be using an Andes processor, and it is a RISC-V type of the variant NX27V. The program I want to run on the Andes processor is the Mobilenet V1 demo L file. And as I was talking, I also invoked the simulator itself by typing in the command line. And it finished by printing out this few lines here. So it's telling me that the number of instructions executed were about a little over 30 million instructions, with the majority of them being vector instructions. And it identified the picture as 483. So if we double back to take a look at the ImageNet 1000 class list, and the 485 says that it is a castle. So Mobilenet did infer the correct image. Next, let's take a look at the configurability of the processor itself. So here I asked the processor by running the same command line, and I want to take a look at what are the parameters that's relating to the vectors that I can give it new value. So, but first of all, I like to draw your attention to the vector version. This is a value that can be overridden on the command line itself. So let's give it a try right now. But I'm not going to override with anything. I'm going to ask it what are the values that I'm allowed to. So at first it's telling me that currently by default it's using the 1.0 draft 2021 January 30th version. So that is the default for this particular version of ISS. But in the simulator for this processor, there's other versions of the vector spec that one can use, including the earlier ones, the 0.7.1 draft version and the 0.8 draft version, 4 of them. The master version is the version that is following the working group's latest specification. As it changes, we keep track of it and put it here. When the working group come up with they formalize a version with a PDF file, that's when we publish, freeze that and publish that as a different vector version that one can use. And we do the same for all the other RISC-V ISA extensions, such as bit manipulation, crypto, hypervisor, and the other ones. Whenever there's a PDF file, we make a new release of it, and you can always go back for various versions. So it means that if your hardware implemented an earlier vector version or earlier crypto version, you can still be able to roll back the Imperas simulator to that version to continue your early neural network development. So you're not always stuck with only the latest specification version. So let's go back and take another look at the vector parameters that you can affect on the command line. Here it is. So we see here at the beginning, so these are the ones, the EEW index, the E-length, S-length, V-length, those can all be changed on the command line, and also the single element width can be changed. This group here are the vector instruction subsets that you can individually configure into the simulator if you have it in your hardware, or just leave them out as default, which is false. They are not pulled in by default. So if your hardware has them, then you should definitely override these particular parameters to true. And also at the end, we have this, you can also affect the non-maskable interrupt vector and the reset vector addresses. So let me show a little bit of Imperas multiple processor debugging MPD tool. So I invoke it with this command here. This is not quite an override, but this is a command line option that I'm telling the tool that I want to invoke the GUI format of the multiprocess debugger. And it will automatically invoke the debugger itself, which is presented in the Eclipse environment. On the left-hand side, here it is. On the left-hand side is the hierarchy of the virtual platform that's being debugged. So in this case, because I'm running a bare metal application, only using an ISS, so this does not have too many entries. It only has an ISS. And in the ISS is a CPU 0 instance, which is an NX27V processor, which is a RISC-V processor. So should the Mobilenet application is a Linux user app, then this view on the left-hand side is going to be quite populated with many entries such as UART, multiple UART sometimes, maybe USB, Ethernet, and interrupt controllers too, like the click, plick, and plint, and whatever other peripheral components are on the hardware platform on which that Linux port is to boot on. So MPD accepts all the GDB type of debugging commands that you can type in the debugging console. But I really want to show you something different, and that is going to go straight into looking at the processor and introspection process into the processor's vector-related registers. So let's pull up the programmer's view, which is a superset of the basic registers view. This registers view is the processor's GDB type of view that you have. It takes a while to bring up, but let's go back to the programmer's view. So it shows you a little bit more than what GDB offers. So first of all, it prompts you what you're focused on, and that is the ISS instance of CPU 0, what type of a component it is. And right now, what is the instruction count? Since when this simulation was invoked, we connect to the MPD Eclipse environment, but I haven't executed any instructions yet. So that's why instruction count stays at 0. And at the moment, it is staying in machine mode. Depending on what you're doing, what's in the application, this may change to supervisor or user mode, etc. And it also tells you what's the last exception. In this case, there's no last exception, but must be some default things that's left over from previous things. So the core, there's after that are different groups of internal registers that you can look at. So by clicking it, you can drill down and see this is basically the GPR of a processor that GDB can give you, stack pointer, GP, TP, and then all the generic A0 to A, all the regular register file registers, and also the PC. For the NX27V, it's configured the floating point as well. So all the floating point register file are displayed in this group. And then the next group down is the vector registers. Notice that they are fairly long. In this case, I'm showing them as hex values, and you can easily change them to binary or other display mode. So you can see all this in one glance. So let's run some simulation. Let's try going for 10,000 instructions. Okay. Let's go back to the vector instruction. Oh, it hasn't got to that yet, so let's do maybe another 1,000 instruction. So here, as you can see, the vector registers are changed. So they're doing some calculations of this Mobilenet. Then I can continue to run some more simulation, 1,000 at a time. So you can see here, I am pausing because I give it a command by clicking this little icon here, resume for 1,000 instructions. So every time I click this one, you'll see that the icon point is increased. So let's do that. And now let's go to 13 and 14 and so on. As I do this, you can see that the vector GPRs are changing because of the various demands of the algorithm itself. Okay. So, but then we also want to take a look at the CSR, the vector CSRs. So we go down to the user control and status group of registers. So we see that. So we see this V start. This one is vector start index CSR, vector fixed point saturation flag, I think, vector fixed point rounding mode, and just vector CSR. I think there's a few more at the bottom of this generic group of user control and status register. This is the vector length register, vector type, and the VLength, the vector length in bits. The next group is machine control and status. So this is status, MISA, machine trap vector, and so on. All these has to do with the exceptions and so on. What are interesting to see here. So there's a lot of things that you can inspect at your fingertip just by a click. Everything is there. And this programmer's view, it can also be focused on a peripheral such as UART, and in that case, it would display a list of the UART's own internal register onto which you can also set a breakpoint. So I think, let's see, it's executed somewhere. I don't know exactly where it is, but let's go into this particular function. Maybe we can put a breakpoint. I don't know where the program is at. Maybe it's past in the very late stage, but let's just put a breakpoint at the very end here. See if I put it there. Yeah, 344. So just let it run, and then it will stop at this point. So it's going to take a little bit because there's a lot of instructions. Oh, I think it was already at beyond that the point that I put the breakpoint, so it did not break. But we can do it again. Let's just terminate and remove it. Okay, let's do it again. Okay. So let's see now. We have these 3 breakpoints set. Might as well just let it run. And so now these are just basic GDB things that you can do. So it stopped at the main, and I let it go again. It will go to the next breakpoint. Meanwhile, I can go back to the programmer's view, but it's running, so I have to pause it in order to really update the view here. I think I'm going to Control C it. Let's see what's happening. The vectors. Oh, as you can see now, the more vector registers are being involved in the calculation. So I think I'm going to end this demo. So I'm just going to let it finish its run. Removed all the breakpoints. And it's finished by printing out that it's executed 30 million instructions. And that concludes my demo today. Back to you, Kat.
Thank you, Manny. It was my first time seeing the demo of NX27V, so it looks really good. So we finished the Imperas section. Now we open to the floor for Q&A. And you can ask questions to any of the speakers.
Wow, no questions. I thought Texans were not shy.
I think we put everybody to sleep.
It's the aloha shirts.
Well, blinded. Everybody's blinded.
Or you got that sun in your background.
Well, that's true. That's from a beach in Hawaii.
Okay, if there are no questions, thank you very much for coming. We look forward to a day when we could do this in person and interact. Stay safe, everyone, and let's have fun designing. The world is waiting for artificial intelligence.
Thanks, everybody.
Thanks, everyone.
Bye.